Okay, so we have talked about accuracy and precision, and we're going to focus a little bit more on precision because in this lesson, we're going to talk about something called uncertainty. Because no matter what kind of measuring device we use, there's always going to be a little uncertainty in our measurement. It's not going to be exact, right? And that could be because of human error, like whatever instrument you're reading to measure, you read it incorrectly, or the instrument just isn't perfectly accurate, okay? I mean, there are some machines out there that are extremely accurate and extremely precise, but I dare say there's none of them that are perfect, okay? So because we can't obtain an exact measurement from any measuring device, we usually want to incorporate some uncertainty with our measurement. And we generally do it like this. When you take a measurement, you write your measured value. I mean, that's nothing new. Except we're going to add something now. And we're going to add, oops, uncertainty. Meaning that this is the value we measured, but there's a little uncertainty that comes with that. It could be a little bit higher. It could be a little bit lower. The question is, how much do we say? Okay. So just as an example, if we consider these two figures, we're measuring the same object, except figure B is a little bit more blown up than figure A. It's more magnified. Do you remember when I say precise? These rulers are precise to what? Remember, you look at the smallest notch. Are they precise to the nearest centimeter? If this is a centimeter, or are they even more precise than that? More precise, because there's notches in between, right? How many notches from 0 to 1? 10. So we could say that this is precise, oops, and this is from the previous lesson. This is precise to nearest 10th of a centimeter, or each of those little notches also represents a millimeter. So that's the precision of these rulers that we see here. Okay? Now, how do we calculate the uncertainty value that we add? Well, what we do, okay, is the uncertainty value is always the smallest scale on the measuring device. And because we want that uncertainty to be in either direction, we divide it by 2. So what this is saying here, the uncertainty is equal to, well, nearest 10th of a centimeter, that's the same as 0.01, divide 2, which gives us 0.00, sorry, do I have that right? No, 1/10. What am I doing here? Oh no, 110. Get your decimal points right. It's 0.1, which is 0.05. Okay? So whatever we measure on this ruler, we write down the measurement, and then we write plus or minus this uncertainty. Okay? So it's plus or minus this uncertainty.
It's always going to be divided by 2?
Always divided by 2. So you take however precise it is, divide it by 2, and then do plus minus that amount. So in this case, we would say, if we measure this, like if we look at this one, looks like it's around 0.95 centimeters. Okay, maybe 0.94, somewhere around there. So we would say 0.95 plus or minus the uncertainty, 0.05. That means that, okay, we're saying we think it's 0.95, but it could be as high as 1. Because if I add 0.05, right? It could be as low as 0.9 if I take this and take away 0.05. So I'm giving myself a range to be more like for my measurement. And that's how often measured values are reported for most part. I mean, like what you guys have done into math at this point, whenever you guys measured something, like say back in middle school or back in junior school with a ruler, you never expressed uncertainty. Okay, you just wrote down what you thought the answer was and you stopped. Okay, but now there is some uncertainty that comes with it. So let's look at a couple of examples. This will make it hopefully a little clearer. Layla measures the radius of a circle and she gets an answer of 28 millimeters. What is the precision? Nearest 1. Nearest millimeter, right? Because there's no decimal points. It's not nearest 10th, it's not nearest 100th, it's nearest whole millimeter. How do we calculate the uncertainty? We take 1 millimeter, divide 2, and that gives us 0.5. So we would say the uncertainty is plus or minus 0.5 millimeters. That's how you calculate the uncertainty. Take the precision, which is 1 millimeter, I'll even put 1 here, okay? Divided by 2, and then put plus minus in front of it. And so what should she report? Well, she should report what she measured plus minus the uncertainty. So that's the final answer. Okay, that's all we have to do for that. Let's try one more of these. What's the precision of this one if Brendan measures his height and finds it to be 72.0? What's the last place value you see? The tenths. Okay, so it's 0.1 centimeters. If there was 2 decimal places, it'd be 0.01. If there were 3 decimal places, it'd be 0.001, etc. The uncertainty, we take the precision, divide by 2, and we get 0.05. Therefore, our uncertainty is plus minus 0.05 centimeters. So how do we write our final answer? Well, we write what we measured plus the uncertainty. So he got 72.0 plus minus the uncertainty. And then your units. Okay. So that's uncertainty and precision. What about uncertainty and accuracy? Okay, well, this is pretty straightforward. Remember, accurate means how close is our measured value to the true measurement value. Okay, that's accuracy. Precision is if we measured it over and over again, would we get similar results or the same results? Well, many times when some measuring instrument is not accurate, there's something wrong with it. So like, remember in the last lesson, we saw that curved ruler. I mean, that's not a normal ruler. So that's not going to give us accurate results. With other machines, okay, if they're not giving accurate results, a lot of times they have to be calibrated, which means that however they go about measuring is somehow off. And it needs to be, in a way, it needs to be reset so it's measuring more accurately. Okay. So let's look at 2 more examples. Oh, it's not this. So let's say we've got a scale, that's our measuring device. And we're going to weigh a baseball that we know is 100 grams. We're going to weigh it 3 times to see if we're accurate, to see if we're precise. And when we weigh it the 3 times, we get 84.523, 84.528, 84.531. Is this measurement device, is this scale precise? What? Really? Remember, precise is if you measure it over and over again, are you getting to the same results? Yes, you are. You're confusing that with accuracy. This is precise because we keep getting, if we do it several times, we keep getting very close values to each other, but we're not getting the true value, right? That's accuracy. So we say it's precise, but it's not accurate. Okay? So it's quite precise because those measured values are very close to each other. Values are close to each other. But not precise, or sorry, not accurate. Lower than true value by quite a bit. Okay? Make sure you understand the difference between those two. And what may cause the measures to be inaccurate? Well, maybe the scale just has to be calibrated. Okay? Something's wrong with the scale, it's not measuring properly, it has to be reset. Okay? Scale may need to be calibrated. Either that or somebody who's really bad at reading measurements, and that's human error. In the last example, we're going to go back to uncertainty. So the accepted measurement for acceleration due to gravity on Earth is this number, 9.8 meters per square second. So Abby completed an experiment designed to measure this acceleration due to gravity by dropping various objects and measuring the distance the objects fell and the time it took for them to fall. After she got her calculations, she got a measurement that was 9.5 plus or minus 0.5. Is the measurement that she got, including the uncertainty, within the actual measurement? Yes, because she got 9.5, which is not the same, but her uncertainty says she could go as high as 1 or as low as 9, which 9.8 is in. Okay? So, yes, because Abby's range with the uncertainty is 9.0 to 10. And 9.8 falls in here. What if instead she found this to be the measurement, 9.5 plus 0.2? Is she within the actual? No, just a little bit shy, right? Because this range goes from 9.3 to 9.7. And 9.8 is outside. So the first one, she was within, second one, she was not. Okay. Okay.